Okay, ladies and gentlemen, next topic. What do we mean by RMS values and why it's so useful? So we start out with the power equation that equals I squared R. You have a certain current going through the through the resistor. And the effective value, the quote RMS value, is the equivalent DC value that supplies the same average power. Remember that the power equation for AC is power equals 1/2 I for sinusoidal waves, I max squared R. Well, RMS makes the equation look like this again. Makes it look like the DC equation again, which is why we go for that. Okay, and I already talked about this right here. Average power over one period. Now, by taking a look at these two equations, you can see, oh, if we define our effective current in this way, the effective current squared equals 1/2 maximum current squared for a pure sinusoid, then we can use the old DC equation. We don't have to memorize new equations. We don't have to memorize this. So, if it's non-sinusoidal, here's the equation. We take the average power is going to be the resistance, the current going through resistance, 1 divided by the period of the wave, periodic signal, whatever that is, square. It doesn't matter if it's square, triangle, sinusoidal. We've already figured it out for sinusoidal. But it can be anything. You integrate one period, I squared dt, divided by the length of the period, and then the power, the average power, is going to be, if you define this as the I effective squared, then the average power is going to be R times I effective squared. DC, if I is a constant, then it's pretty easy to see this is RI DC squared. I effective is IDC. Here's another way to express it. Okay. Taking the square root of both sides. Now you can see why they call it root mean squared. The integral divided by the period is going to be the mean of the square, and then you take the square root of that. For a pure sinusoid, a signal, some sinusoidal signal, the root mean squared signal is given by this for a pure sinusoid, just like up here. Power, you can take the RMS values. You often hear, instead of effective, you hear the term RMF a lot. And of course, this is the difference in the phase angles between the two. Effective RMS, excuse me. Root mean square. Okay, so a couple examples here. So we have a periodic signal. Period is 3, so it does this and then it repeats itself again, keeps going. And so we want to know what the RMS value of this waveform is. We take the integral of the from 0 to 3 of v squared. Well, from 0 to 1, so this is the square of the root mean squared value. 1 over t, capital T, times the integral 0 to 1 of, well, v is just going to be 4t let's see, 4c squared dt, and it's v is 0 for a while from 1 to 2, plus the integral from 2 to 3 of, now we have to, we're starting at 2, so voltage is 2 minus 4t, voltage squared would be this, dt. 2 to 3, okay. So that's going to be equal to V RMS squared. And I've got a problem here. I've got a problem with this one. Let's cross that off. The voltage is going to be T minus 2 squared. There we go. So when time equals 2, then it's 0, like it's supposed to be. When time equals 3, that's 1, and I need a 4. There we go. That's what I got wrong there. Put a double parentheses there. We'll see that by doing a substitution, say t prime equals t minus 2, dt prime equals dt, we can see that the integral from 0 to 1 is equal to the integral from 2 to 3, just doing the substitution. So just doubling that. The integral from 4 squared is 16, and then that'd be t cubed, which is 1 cubed, 1/3. So it's 32 thirds over 3, so it's 32 over 9 equals V RMS squared. Okay, just remember that. I'll put it up here. And I'll pause for just a second and do some erasing and stuff. Okay, let's see what the book says. So, one period, 0 to 3, just like I said. These functions and again, there's the two integrals, the v squared dt, and I wrote down, I made a mistake at first and Ben corrected it to this form. They have the same value, do the variable substitution there. And the integral v squared is 32 thirds. You divide that by the t of 3, you get 32 ninths for the RMS value squared. And they take the square root and go for the final value. Voila! Not too tough. Okay, now this is this is not too tough. This is like a piece of cake. because you'll notice there's no DC offset. It's symmetric. It's up to 4 and it's down to 4. When you square it, you'll get a current of 16. Yeah, I squared is always 16. When it's positive, it's 16. When it's negative, negative 4 squared is 16. Period length, the period is 4 seconds. So that's pretty easy. It's almost like the DC case. The average power, RI squared, 16 times 2, or 32. Okay, stopping here. I'm going to let you guys do this one. We'll pick up after this. Let you guys do some examples.